This lesson will identify frequent indications and causes of system malfunctions for many aircraft. Many malfunctions can be identified early and corrected before an incident or accident occurs through active monitoring of systems by the flight crew and active communication of system status and deviations between the captain and first officer. This lesson will stress the importance of continued training and practicing by pilots to maintain appropriate responses and to lessen the effects of potential startle and surprise scenarios. The following objectives will be covered during this lesson. Identify the purposes of continued practice and training relating to system malfunctions for pilots. Describe the manner in which active monitoring and upset prevention and recovery training can prevent developing malfunctions from escalating to full incidents or accidents. Explain some of the most common causes of malfunctions on aircraft and how these can be mitigated through proper training. When flying near the edge of the flight envelope, often during cruise, aircraft system malfunctions have proven to be significant causal or contributing factors to aircraft accidents. This is usually due to their surprising and/or startling nature. Pilots learn and then practice the procedures for a multitude of onboard systems failures before they ever fly the actual aircraft. On a recurring basis, pilots continue practicing more systems failures. Simulator training effectiveness is largely in the performance of procedures at the expense of flight continuity. Loft sessions provide training that is closest to real-world environments, but there are few demanded by training directives. Training in specially certified simulators with specially trained instructors by use of realistic upset scenarios is a goal of Upset Prevention and Recovery Training, UPRT, in addressing the issues of surprise and startle. The primary objective of this training session is to provide pilots guidance for managing aircraft system malfunctions which may cause upset conditions. This lesson will consider flight control defects, full or partial engine failures, instrument failures, automation failures, fly-by-wire, FBW degradations, stall protection and icing systems failures, and flight with unreliable airspeed. Mechanical failure of flight control systems is quite rare. When failure occurs, it can directly and very quickly cause the aircraft to leave the desired state. Examples include runaway trim, asymmetric flaps, and failed or binding flight control elements. The aerodynamic effects of all flight control failure possibilities cannot be programmed into simulators. Aircraft manufacturers provide the best type-specific guidance for flight control failures within the aircraft operating manuals. Active monitoring will observe and respond to system enunciations as they occur, but many flight control failures are not enunciated. Like flight control system failures, engine failures are rare events. Pilots train for engine failure more than any other type of failure, so expectations are that an actual occurrence should be a well-managed and well-executed procedure. These expectations have generally been realized. However, engine failures do indeed cause upsets that lead to loss of control. Historically, simulator training of engine failures, although common, fall prey to the same issues of most maneuver-based training events. Context and continuity of flight phases are most often absent. Additionally, the overwhelming number of simulated engine failure scenarios are in the traffic pattern or otherwise at low altitudes. High-altitude engine failure training has been relatively rare. Active monitoring of engines includes visual inspection of engine parameters and enunciations, as well as some other systems enunciations. Simple flame-out conditions at high cruise altitudes can be surprisingly non-dynamic. Many pilots have reported first signs of a flame-out as being either large control yoke displacement or engine electrical system advisories. This indicates that engine rollback and the subsequent automatic power increase of remaining engines with associated automatic rudder control application can be a dynamically mild event, especially on aircraft with 4 engines. Not all engine failures are as benign as flameouts. Monitoring the engines also includes hearing and touch. Most aircraft operating at lower altitudes and lower airspeeds enable audible recognition of engine failures not associated with a fire or overheat condition. Engine fire and overheat notifications will have visual advisories accompanied by audible alerts. Compressor stalls and compressor or turbine disintegration will be audible and will offer tactile sensory input as well. In all cases of engine failure, apply proper standard operating procedures, SOPs, using threat and error management, TEM, and crew resource management, CRM principles. Aircraft are designed to ensure that pilots have at least the minimum information necessary to control the aircraft safely. The AUPRTA app notes that accident reports reveal pilots are not always actively monitoring to correctly analyze the situation, and an upset can develop. A pilot may consider monitoring as investigating the aircraft state through instruments, though a better understanding of active monitoring exists when a pilot takes it to the next level. After viewing the aircraft's instruments, active monitoring seeks out additional relevant information while not wasting time on irrelevant information. Active monitoring allows the pilot to observe other instruments and the Integrated Standby Flight Display, ISFD, to compare three sources of information against each other. This active component of monitoring provides a valuable error isolation function, and any unexpected observations should be communicated to the other pilot. Some instrument in-op flags or annunciations command less visual attention than others. This still holds true with modern instrumentation. Many pilots have reported observing an instrument with degraded or failure indications and not seeing the indication. Many of these were reported as occurring absent from startling events. Roving eyes do not always mean there is data entering the mind. Consider active as an active mind, or thoughtful and monitoring as scanning physically with the eyes, ears, the nose, and hands. Actively monitoring instruments is purposeful, deliberate, and inclusive in order to communicate discovery and analysis to the other pilot. The term autoflight systems covers the autopilots, autothrottles, flight management, and guidance computers, and all systems which input data to the computers for flight management. There is a pilot-aircraft interface paradox which has been developing for many years. The automation intended to reduce pilot workload has a negative effect by essentially removing the pilot from higher-level management of the aircraft state. The better and more reliable automation become, the more a pilot comes to trust automation. After trust is attained, dependency can develop. After dependency, any number of automation malfunctions can create startle or surprise, resulting in loss of control in flight, LOCI. As presented in the introduction to UPRT, a new global cooperation has investigated and evaluated the rising fatalities in the past 2 decades. The results of this massive and continuing endeavor are the new evidence-based strategies in training and SOPs being presented by UPRT. IATA reports that pilots do not always comply with SOPs, even though the safety and operational benefits of compliance with published SOPs has been increasingly emphasized. Verification by cross-checking, followed by continued active monitoring, are 2 critical parts to any procedure designed to establish and maintain the desired aircraft state, as well as reducing the incidence of pilot error-related desired state deviations. Lack of autoflight mode awareness comes in the forms of not understanding the systems and not incorporating flight mode annunciators as monitored elements. A common CRM requirement is that all changes to how an aircraft is being controlled should be coordinated between pilots, and many operators require a call-out for the action. Failure to comply with SOPs can be symptomatic of crew laziness or failure to mentally assign a procedure to a discovered situation. Since following practiced procedures is easier than making one up on the spot and following it, laziness does not explain creating ad hoc operational procedures. This is more likely to occur due to arrogance and ego, or possibly confusion. Verification, cross-checking, and monitoring are all subsets of aviation SOPs. When they are ineffective, it is typically due to laziness, an incomplete understanding of how these concepts fit into the SOPs, or distraction. Distraction may also cause a lack of autoflight mode awareness. Desired course intercept after a weather deviation may not occur if, after deviation and on intercept heading, LNAV is not armed. It also may not occur if pilots are not actively monitoring flight mode annunciators, FMAs. Failure to communicate flight mode changes to the other pilot is a setup for deviation. Essentially, most automation failures are typically proven to be pilot-induced. Normally, standard operating procedures have been worked out for most possible aircraft situations. Usually, standard operating procedures are effective. But remember the Air France A330 flight from Brazil to Europe. It was not working for the pilot flying to hold back the flight control stick to try to arrest the descent. The benefits of using automation after an aircraft departs the desired state are time-sensitive. The earlier a deviation is observed, the sooner corrective measures can be decided upon and applied. If a deviation is minor, corrective action to return to the desired state is small and may be better accomplished with the autopilot. If a deviation continues such that it places the aircraft at the fringe of the flight envelope, the challenge to return to the desired state may exceed autoflight capabilities. Be aware that the decision process to continue with automation or to disable increases the time and magnitude of the deviation. In presenting common errors to avoid, it was noted that if pilots are distracted, SOPs might remain incomplete. These can be rectified before undesired states occur if proper monitoring skills are present and active. Insufficient auto-flight systems knowledge is often observed as a cause for undesired states. Data input tends to be the most common type of automated flight management error. It is always important to include verification and cross-checking with auto-flight SOPs as faults occurring from data input errors are assigned to the crew. Some modern aircraft types have FBW primary control systems with built-in protections which prevent the exceedance of critical flight parameters and which can ensure recovery without manual response from the flight crew. However, flight crews must clearly understand that certain system failures can degrade these protections such that the aircraft is left with reduced or no protections and become, in effect, a basic aircraft. Generally, the degradations are layered such that original equipment manufacturers, OEMs, can ensure effective control authority and protection as required data for flight computers is lost. When FBW systems are in normal mode, full system design functionality is available. As specific input data to computers is lost, or as the computers themselves fail, secondary or alternate modes will be applied to degrade protections while retaining or transferring control authority. Mechanical backup is available, but it is not designed for landing the aircraft. Recent accidents have revealed evidence which strongly suggests not all pilots understand the FBW control systems of their aircraft. Many OEMs offer aircraft with FBW control systems. These systems are complex and detailed, so their understanding is critical to safe flight. Due to OEM differences with logic and design application of FBW systems, pilots should refer to their aircraft operating manuals for system explanations and study. EASA Safety Information Bulletin, SIB 2013-02, identifies the training methodology requirement to include operation and function of stall protection systems in normal, abnormal, and emergency situations. Additional specific requirements from this safety bulletin include training failures of the icing alert system, as well as the hazards of overriding or ignoring stall protection system indications. Pilots normally use all available information from all useful sources to remain in normal flight conditions. Normal situations allow pilots to manage flight progression from a position of confidence established by training and experience. Well-disciplined pilots actively monitor their aircraft, and upon discerning a stall warning system has failed or is expected to fail, the appropriate SOP is called for without delay and completed to include departing icing conditions. The key here is to prevent the threat from developing further, thereby destabilizing the aircraft state. The simplest abnormal situation starts with a divergence from the desired aircraft state. Actively monitoring crews will observe, verify, and communicate the issue, followed by making an appropriate control adjustment and applying any applicable SOPs. Some abnormal situations are very challenging and can divert attention from flying the aircraft. If a crew receives a stall warning system failure indication during the accomplishment of a non-normal procedure, an immediate but brief reanalysis should occur while a pilot continues to fly the aircraft automatically or manually if required. It may be prudent to reprioritize by holding the current checklist and immediately complete the appropriate SOPs for the stall warning or indication. After that checklist is completed, both pilots should ensure the first non-normal checklist is returned to and completed. There could be a case where a crew is currently contending with an emergency. If a stall protection system fails, before doing anything else, the crew should ensure that the pilot flying continues flying the aircraft and any immediate recall checklist items are accomplished. Next, evaluate and prioritize procedures. If icing conditions exist and a fault in pitot heat occurs, delaying the newly required checklist a few minutes to complete another checklist could place the crew in a position where the checklist for flight with unreliable airspeed must be accomplished. Clearly, this is not a good situation for an aircraft already established in an emergency. If an ice alerting system failure occurs, continue flying the aircraft, accomplish the appropriate SOPs, and exit icing conditions as soon as possible. If the failure is in the pitot heat system, after that checklist has been completed, consider referring to the procedure for flight with unreliable airspeed. The sooner a crew has a plan for this challenging possibility, the better prepared they will be to mitigate the effect of surprise or startle if it occurs. A recent audit of Uprt has revealed some success with improving pilot performance during simulator upset training maneuvers. However, a glaring weakness was observed as over 70% of pilots failed to properly recover the aircraft after a loss of reliable airspeed. Losing reliable airspeed has shown to cause startle among many pilots, and preparation by way of study and planning is the best solution to change this truth. Significant to this procedure is the directing of pilots to charts which offer target power and pitch settings for multiple phases of flight. Not all operators place these charts within the non-normal procedure. This SOP is certainly worthy of frequent chair flying. In summary, this lesson has provided guidance for managing aircraft system malfunctions which may cause upset conditions. Covered topics included flight control defects, full or partial engine failures, instrument failures, automation failures, stall protection and icing systems failures, and flight with unreliable airspeed. Next, let's answer some questions.